Hello everyone and welcome to K-means for Dimensionality Reduction, explained for beginners. I'm your instructor Kashif Murtaza from AI Sciences, and in this video we are going to talk about one of the applications of K-means in the field of dimensionality reduction. Most of you might have seen K-means as a clustering algorithm and might be thinking that K-means is only used in the domain of clustering, but it has several other applications. For example, dimensionality reduction, for example, sparse coding, dictionary learning, and several applications. Today we are going to touch on dimensionality reduction. Although dimensionality reduction has several other methods as well, for example, principal component analysis, subspace learning, submanifold learning, there are several ways. Today we are going to see how K-means can be used to reduce the dimension of the data, and it will be very fascinating and very simple way to reduce the dimensions of the data using K-means algorithm. So in particular, first we will talk about what is the result of K-means, what K-means actually do. Then we will see what do we mean by dimensionality reduction, just as a refresher. And then we will discuss two methods. One is distance feature extraction using K-means, and another one is subspace projection using, again, K-means, because these centroids, they are learned from K-means. And finally, we will wrap up our video by implementing both of these methods using scikit-learn in Python. So if you are new to our channel, at AI Sciences, we deliver artificial intelligence and data science consultancies, courses, and services, including online courses, books, and consultancies, lectures, and all the stuff related to artificial intelligence and data science. And if you are a regular listener or regular viewer of our channel, then you're also welcome to another fascinating video on the platform of AI Sciences. So let's start. First of all, let's discuss what is K-means. By the way, if you are interested in finding out the details of K-means, we have another video on our channel that describes the working of K-means in detail with the code examples. So in the description you can see the links, and if you subscribe to our channel, you already will be having updates. And in our channel we already have uploaded the K-means video that actually explains the details of K-means algorithm. Here I'm just going to tell you what K-means actually does. So let's say you are given a lot of data, and these are data points. This is data point, this is data point, a lot of data. And there is no membership of any data point into any group. So what K-means really does is tries to group the data and assign membership of every data point to a particular group. Under the hood, what it does basically is it actually computes the representative points, like this is a representative point. How it computes, it has algorithm, obviously, and you can find out the details in our other video on K-means. So it computes the centroids or the representative points. In this case, it has computed 3 centroids. And whatever the data point that is closest to whichever the centroid, the data point is assigned that group. So you can think of these centroids as representatives of the group, different groups. So given a lot of data, not necessarily just in 2 dimensions. Think about the data maybe in several dimensions. Let's say this is xi1, x1i, x2i, x3i, and so on. Maybe we have xdi. Maybe our data point really belongs to a d-dimensional space, which really means each data point, let's say xi, has d features. We call it that the data point actually belongs to a d-dimensional space, or the feature space has d dimensions. So data can have a lot of dimensions, and we can have a lot of such points. For example, xn. Starting from x1 to xn, we can have a lot of such points. Then the centroids that we will be computing will also be some points in that d-dimensional space. Not necessarily the points from the data set. Maybe the centroids are being computed in a way that they are not the points from your original data set, or maybe some of the centroids are indeed the points from the data set, but that's not a restriction for centroids to be the points from the data set. For example, if we set k centroids, let's say k is equal to 3, so the result will be 3 centroids. Let me draw them in different colors. Centroid 1, let's say, and then we may have another centroid, centroid 2, and then we may have another centroid, let's say, and maybe green color, centroid 3. So these are the centroids. Obviously, the clustering algorithm then performs will compute the distance of every data point from every centroid and see which centroid is the closest one. So you can think of these centroids being representing as the groups of the data to be formed. So that's what is the result of k-means. Now let's see, what do we mean by dimensionality reduction? So think of different data points. Let's say in this particular case, we have a lot of data points like x1, x2, x3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and in this case, we have 14 data points. And each data point has a lot of features. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. In this case, the number of features are also 14, but that is not the case always. You may have a lot of data points with few features, or you may have a few data points with a lot of features. So dimensionality reduction aims to get new data points. Let me call the new data points as x dash 1, x dash 2, to x dash 14. New data points, but the data points really have small number of features as compared to this number 14. Maybe all the data points have only 5 features. And those 5 features may or may not be exact values out of these features. They may be different values. So let me represent them by some stars like this. These are 5 real values. x2 may have 5 real values, and these values may be different. And similarly, x14 have 5 values, and all these 5 values, they may be different from the other x1 dash and x2 dash and so on. In this case, we have reduced the dimensions from 14 to 5. Well, how to do dimensionality reduction? There are a lot of ways. Actually, we have a full-fledged course on dimensionality reduction and feature engineering. If you see in the description, you will find out the links, and we have explained that in detail. So there are a lot of ways of doing this dimensionality reduction. Obviously, one way is better than the other in certain situations, and so on. There is no general best way, but there are task and data dependent choices that one can make. So the result of dimensionality reduction is the data having same number of points, but each point represented with fewer features rather than a lot of features as originally. So in this video, we will also see one method using k-means for doing this stuff, doing this dimensionality reduction. So let's talk about it. First of all, as we saw earlier, let's think about that we run the k-means clustering algorithm, k-means algorithm, C1, and let's say we end up computing 3 clusters. Let's say we aim to reduce the dimensions from 14 to 3. Let's say 3 clusters. Okay. Now, what we do, each of this centroid also has 14 features. So this particular centroid has 14 features. This particular centroid has 14 features. You can think of all these centroids are just ordinary vectors with 14 real numbers represented in a column vector. Now what you do is this is your x1. So let me generate x1 dash. So what you do is you pick this x1, the whole vector, you pick this whole vector, and you take its distance from C1. You can use any distance metric, but let's say we use square distance, which means you pick the very first value, 54 in this case, and the very first value, whatever the centroid first value is, you subtract them, take their square. You pick the second value, and the second value from here, subtract them, take their square, and so on. So after that, you will be having 14 subtractions and their squares. Now you add them up, you will be having one number at the end of the day. If you add all the squares of differences, you have one number, and then you take a square root, which is finally give you a final number, which is called the L2 distance or Euclidean distance. In that case, this number will be representing, let's say 31, maybe 31, will represent the distance of this first point from the first centroid. Now you compute the distance of the first point from the second centroid, and whatever that number comes, you write that number, let's say 5. And then you compute the distance of x1 from the third centroid, and whatever that number comes, let's say 41, you place it there. The numbers may be in real form, for example 41.6. That's okay. Now if you repeat the same process for x2, which means you pick x2 independent from x1, and you compute its distance from C1, then from C2, and then from C3, and you get 3 numbers, and you place them here. Now what essentially you are doing is you are using these centroids, and the distance of centroid from a data point is used as a new feature. And now your data, the dimension of your data is reduced from 14 to 3. Now the number of clusters really tells what is the new dimension. So the algorithm is really very simple. You get your data, you apply k-means on that, find out the representative points, which are the centroids. In the second pass, once you have centroids, now reiterate over the data, pick each data point, compute its distance from all the centroids, and all these distances, these are actually new features. Now if originally you have, for example, 100 features, and you have only 5 clusters or 5 centroids, then the new features are only 5, the 5 distances. And do it for every data point, and that's one way of dimensionality reduction using k-means. There is another way. Another way is the subspace projection. This is really, actually, I should call this is really PCA, what I'm going to explain. But the differences, I will highlight the differences of PCA and this method. What you do again is the following. Let's say you have original data and you compute some clusters, let's say centroids. Let's say 4 or 5 centroids or whatever, let's say C1, C2, C3, C4, and C5. Now what you do is you make a vector space out of these centroids. You think that these centroids C1, C2, C3, C4, C5, they span a space. And actually that space has maximum dimensions 5. Why I'm calling maximum dimensions 5? Because there may be linear dependence between the vectors, and maybe some of the vectors are redundant linearly. And so the dimensions may be, the actual dimensions may be smaller than 5. But the maximum dimension at the end of the day is 5. Now what you do is you can compute the orthogonal basis, the perpendicular. These vector centroids may not be perpendicular, may not be linearly independent either, but you can compute the orthogonal vectors out of these vectors. Let's say the orthogonal vectors are C1 dash, C2 dash, C3 dash, C4 dash, and C5 dash. Let's say these are orthogonal vectors. And by the way, if these vectors are not all linearly independent, then the number of orthogonal vectors may be smaller than 5, maybe 4 or 3, depending upon how many linearly independent vectors are there. So step 1, you compute the centroids. Step 2, you orthogonalize them. There are several ways of orthogonalizing the vectors. One quick way is to use SVD, or you can use QR decomposition, or there are several ways. In the code today, we have used singular value decomposition to do that. Now, the next thing is the following. Let's say you have x1, your data point, this data point. What you do is you take its dot product. Rather than computing distance, you take its dot product with C1 dash, and that's a new feature. Dot product, that's a new feature. Now you take its dot product with C2 dash, and that's an other feature. And similarly, if you have 5 centroids in orthogonal form, or you have converted them in orthogonal form, you'll be having 5 new features representing x1 dash. Similarly, you do it for x2, x3, x4, and so on. The difference of this method with PCA is that in PCA, we do not use all the orthogonal vectors, but we may actually can drop some of the vectors as compared to the others. In PCA, we also have a way of choosing out of these orthogonal vectors, we have a way of choosing which vector is important than the other one. But in this method, we choose all the vectors that are orthogonal regardless of their choice. Although there is a strong coupling between PCA and this one, also PCA is applied directly on the data and not on the centroids. But this actually, you can think of this method as first computing centroid and then applying PCA on that to reduce the dimensions. And that method is known as subspace method. This method also has different names like centroid QR method and things like so. So let me summarize. First of all, if you want to do dimensionality reduction using k-means, first of all, you have to compute the centroids using k-means algorithm on your data. Now you have 2 choices, for example, at least 2 choices. You may use distance measures for the features, or you may use the dot products for the features. If you use distance measures for features, you directly compute the distances of your data points from the centroids and use those as features. If you want the dot products, then you first have to compute the orthogonal basis or the orthogonal centroids, and then you use the dot products as features. Both 2 and 3, both of these methods, they will give you a small number of features, and your dimensionality will be reduced to exactly the number of centroids. In the later case, however, in case 3, if your centroids are not all linearly independent, then your dimensions will be even smaller than the number of centroids. So that's the summary of the whole video. Let's see the Python code, one of the Python code that explains all these things. Let's see a classification problem in that regard. So let's load the data, load digits, and that has get data. Let's make an alias get data. K-means, that's a classification data. Let's use a singular support vector machine classifier or some other classifier, doesn't matter. Train test split for evaluation, and this is for SNS, Seaborn, and PLT for confusion matrix plotting, and NumPy we always need NumPy. Okay, so this is the method that actually uses the, this is the function that actually reduces the dimension based on distance features. What it does is it takes the data matrix and the matrix of centroids, where each row is a centroid. And then for each centroid, it computes the distance of all the points from that centroid, and those distances, they actually form a new feature vector. And at the end, because we are appending this in a list, at the end we just return that as a NumPy array. The second method is subspace projection. Again, you have the data and you have your centroids from k-means. And what you do is you apply SVD on your centroid. You compute your orthogonal centroids, so-called orthogonal centroids. And then what you do is you just project the data using dot products. and that's your new features. So either you use the distance features for dimensionality reduction or the subspace projection, whatever you want to do. So let's run this one by one. These are just function definitions. That's our data. If I just show you the shape of the data, that basically is, it has 64 features. Actually, these are 8 by 8 images flattened out. So we have 64 numbers for each image, and there are a total 1797 images. Next, I have used this flag variable, is subspace method false or true. If we take it this true, then we will be using dot product as features, or we will be using subspace method. If we take it false, then we will be using directly the distance measures. And that's the new dimension we really want to find out. For example, 64 is the original dimension. What is the new dimension, or the value of k, or the value of number of centroids that we really want? In this case, I have set them to 30. Let's split the data into train and test, and let's apply k-means on the data. If you see the centroids, all of them, now we have 30 centroids. Each centroid has 64 features, just like the number of features of the original data. Now, if we have used the subspace method, then it will call the function subspace projection, otherwise distance features, either way. So that's our reduced data. If you see the reduced data, it has 1437 examples, and total number of features are 30. Now let's train our support vector classifier on it, and then apply the same feature extraction or dimensionality reduction on our test data. And that's our prediction. Let's draw the confusion matrix for evaluation. And here you can see it's a pretty good result on this data. This is when we use the distance metric, or the distance as features. Let's use the dot products as features, or the subspace method. Okay, let's see the result in this particular case. And the result is expected to be maybe similar, maybe better in certain cases, but we have no way to choose which one over the other. But you can see very promising result in this particular case. Very, very few errors, and a lot of good things. By the way, you can play with a lot of hyperparameters. For example, what is the new dimensions? And I mean, there are a lot of parameters that you can play with. So that's about it. That's about how can we use k-means clustering algorithm for dimensionality reduction. Again, I would say k-means has a lot of other applications as well. In this video, we have talked about how can somebody use k-means for reducing the dimensions of the data. So I hope you have liked this video. If so, please press the like button, subscribe our channel, and share this video with your friends. Hope to see you next time.